Reyes and Mr. Basil will be doing the second presentation. So I'll invite Dr. Miller.
Thank you, Kamal. Good morning, everybody. It's back to the old blackboard and chalk to talk about vertical control. Vertical control in Trinidad and Tobago. I'm going to start with the history. I'm going to say something about the problems with what little remains of the vertical control that was established. I really want to get on to a way forward, what the rest of the world is doing, best practice, and the way forward to re-establish a reasonable vertical control data nationally. I'm not talking about your local survey that connects to a drain. We need vertical control nationally. It used to exist. This is where you run the main drains to the sea. There's more and more people doing modelling of coastal regions for flood hazard assessment, modelling of watersheds. We've now got things like LiDAR and these modern fancy toy airplane things that are capable of collecting high accuracy data in the vertical component, and yet we've got nothing to tie it to at a national level. So really we need to start thinking about a new reference range for national control. So where have we come from to get to a point where we've got next to nothing? 1850s, TGR, Trinidad Government Railway Data was established to put in the railway line. They needed vertical control. 1920s, that was expanded nationally to give us a national control network. Not quite so national, but it was expanded and it was used at a national level. So the Trinidad Government Railway reference was used nationally. 1938, sea level was established. 3 months of data were required in Port of Spain. Late 1950s, the United States, who were operating in Chagaramas, did 2 years of sea level observations and agreed that mean sea level, as it was established in 1938, was reasonable. So there was a reasonable reference for sea level established. Late 1960s, there was a complete redefinition of the vertical control based on sea level for the mapping exercise that was undertaken in conjunction with the Directorate of Overseas Surveys. My friend Arnold there tells me that when they adjusted the network, the main loop that ran around Trinidad, it misclosed by 4 feet. And that was adjusted out. So we've got some inconsistencies in the original datum that was established in the first place, or the datum that was established, the last datum was established in the late 1960s. Why did that occur? 2 things go wrong. If we take sea level, which we use to define the reference surface, and then think of the land mass that we're using to make our observation from. We start at sea level, and we take levels, so we determine height differences between points to establish survey marks. So we're basically looking at level differences. The first thing that goes wrong is that height, officially, formally, is defined as the height of a point above the geoid, and we're using mean sea level to estimate the geoid being a uniform potential surface. What happens to this geoid under the landmass? Well, it doesn't quite look like that, because we've got this land above them. So the geoid is going to actually lift because we've got a mass above this reference surface that we're using. So what we ought to do when we take these levels is we ought to be observing gravity. So we ought to be using our level to get height differences, and we ought to be using gravity observations to correct those height differences, because the geoid is actually disturbed under the landmass. So you're going to invest $3,000 in a level and $100,000 in a gravity meter. Doesn't actually make much sense, does it? So the first issue is that to do it properly, we would And to get it uniform to the geoid, we would actually need gravity observations. They're doing that in places like Finland, but nowhere else in the world is bothering. They like to do things properly up there. And they're taking years and years to fail. The second problem that exists is that if you think, when you set up, each time you set up your level, you're setting it up on a level surface, and these level surfaces are not parallel. So when you set your level up here, you're setting it up at a tangent to that level surface. When you're setting it up here, you're setting it at tangent to that level surface. And these two level surfaces are not parallel. So when you think about putting a staff here, you're using this level surface and getting a staff elevation there. Then you set up here and using this level surface, your backside to this staff is using a different reference because these lines are not actually parallel. You're not really measuring this height difference up here on the staff because these lines are not parallel. If you look at what goes on in Trinidad, we've got the northern range. We've got out in the Gulf of Paria, down southwest Trinidad, there's a huge hollow which is just filled with sediments. We've got a huge change in the density of the mass that makes up the land across Trinidad. This huge change in density is going to give us a lot of disturbance to these level surfaces because that's what the place is mass of the land. So the reason that the level loop is closed by 4 feet around Trinidad has nothing to do with these fellas that made their observations wrong. In fact, I'm sure they were highly precise in the way they went about their measurements. There was 2-way level loops run. They were closed to the right tolerances. Everything was done properly. The reason they got a 4 feet misclosure around Trinidad was because of the news gravity factor. And because there's no way that you can accommodate the variation in potential surfaces, the fact that they're not parallel, there's no way that you can compensate for that. So the problems that existed in Lebanon and around Trinidad was due to the nature of the land mass that makes up Trinidad, and not due to the observational processes that went on. What's happened since then is that the level marks, most of them have been destroyed because they're all established along the communications routes, which is where people build roads and houses, so they disappeared. We went looking for marks along West Trinidad and found half a dozen. Sea level has risen by about 0.15 of a metre since it was established in 1938. So our sea level reference is about 6 inches adrift. There's a huge amount of land information across Trinidad. Look at the Central Range. You drive from here, cross through Claxton Bay, and you go through these hillsides, and that's where there's a lateral strike slip. Lateral strike slip, yes, it's moving sideways, but it's also causing compression. And that's introduced an uplift that we think it's about 1 centimetre a year. Incredible amount of uplift. And yet other parts of Trinidad are actually subsiding at about 1 centimetre a year. So since 1960s, when the network was established, some of the points have moved vertically by about half a metre. So even those that do exist no longer relate to mean sea level that was there at the time. So we've got destruction of points, variation in sea level, variation in the elevation of the landmass. Means that the little that does remain of the system that was put in place no longer reflects the true height anyway. So it's time to start again. How do we start again? Modern height datums, these problems existed all over the world, similar issues. And nobody really knew what to do about it. And there they were in Europe, messing around doing levelling and gravity, and they probably still are, and they're actually getting nowhere because it's such a long and complicated process. So, and New Zealand had a particular problem. New Zealand, they didn't have a national vertical network. They had lots of little vertical networks where people lived. So in populated areas, they would measure sea level, they would have a vertical network. Somewhere else, they would measure sea level independently and have a vertical network. They didn't have one uniform national vertical control network. And there was no way of putting one in place. There was no way of integrating the different networks that they had. So they decided to start from scratch. They said, what if instead of we using levelling and sea level, let's use a real potential surface as observed using satellite data and gravity data on the terrain. So instead of using levels, let's use perturbations to satellite orbits to measure the Earth potential, and let's use gravity data that's been observed on the terrain and construct a potential surface, and then relate that to the spheroidal surface that we're using for our horizontal control. So they have potential surface, we'll say it's the geoid, but it's not actually realised using mean sea level, and they have a spheroidal surface realised by New Zealand geodetic datum of 2000, which has come about using their GPS course stations. And then what they do is they provide the separations. So they provide a model across New Zealand on a grid. So they have a grid with New Zealand sitting in the middle. I can't remember what New Zealand looks like, I know it's 2 islands. And they have a grid saying, in each one of these cells, the difference between the geoid and the spheroid is this amount. In order to produce this, they made in excess of 40,000 terrestrial gravity observations. Colossal amount of real gravity data they observed across the terrain. They make the grid freely available in various formats. And then a surveyor with GPS can go out anywhere in New Zealand, get their GPS point, get their GPS height, convert it to orthometric height using this geoidal model. What about a surveyor using a level? Well, a surveyor is using a level, can level from a known point to some other point. Only then they face this problem of the fact that the geoid is undulating, the fact that you need to correct for the undulations of the geoid due to the land mass. And we don't want people to use a gravity meter. So they use what's called normal gravity. So they produce a correction to the level observation called a normal-orthometric correction. Instead of being derived from gravity observations, that comes from the gravity field of New Zealand spheroid. GRS8 spheroid is what they adopt. Has got a gravity associated with it. So you look up the latitude, you can get a gravity point relative not to the landmass but to the GRS8 spheroid, and you get this thing called a normal orthometric correction. It's simply a matter of calculating the number and adjusting your level accordingly. So gravity data enables the surveyor who's got GPS equipment to be able to calculate orthometric height by applying a grid, piece of information from a grid. Somebody who's using a level, once you've got an absolute point, which can be established using GPS, can do your leveling, you can apply this normal orthometric correction. Sounds complex, but it's actually a very simple calculation. One number you've got to calculate how it applies to your level data. So they have what they call a normal orthometric system. Australia was a bit different. Australia is a bit more difficult to go and get all the gravity data. But what they did have was levels. They had acquired about 100,000 kilometres of levels since 1945. So what they did was they said, okay, let's take our landmass of Australia, I can't remember what that was like either, it's something like this, and let's put in tide gauges around the coastline and run them concurrently. So they've got 3 years of concurrent sea level data from 30 tide gauges. That gives them a realisation of a potential surface. And then they've got all these level loops that are run between these tide gauges. 100,000 kilometres of level loops. Adjust this level network, applying this normal orthometric correction. So take your level height differences, apply the normal orthometric correction, and then at key points, get GPS data. So the level loops with the normal orthometric correction will basically give you a realisation of a potential surface which is fixed at these 30 tide gauges. And then with the GPS data superimposed on top of that, you can construct exactly the same model, a grid of differences between orthometric and spheroidal heights. So once again, anybody can go out and use GPS and apply the grid value to get orthometric height, or you can go out with your level, and once you've got it marked to where it's wrong, you can do your leveling and apply the normal orthometric correction. So there's two ways of constructing the geoidal model. One is through tide gauges and leveling. The other way is through gravity data. And this is the modern way. Since New Zealand and Australia started, Canada have followed suit. They now work on a geoidal model as their reference for heights. United States are going to go down this path in 2020. They're currently getting the gravity data and that relies necessary to construct their model. So what about Trinidad? There's actually 3 ways of dealing with this. One is terrestrial gravity data. I think you would need about 700 points on about a 2.5 kilometre grid. That's roughly the grid spacing they used in New Zealand. When they did this in Mexico, they actually used a 5 kilometre grid. Mexico's somewhat larger. So we could go out and get about 700. I'm talking about Trinidad, not Tobago. We could go out and get around 700 gravity points, and they need to be uniform, not exactly 2.5 kilometres, but you don't want them all on the low-lying lands. You need as many up in the northern range as you get in the low-lying lands. So it's quite a task to actually go out and get all that gravity data up in particularly up in the northern range. It was also a challenge to Taiwan. They decided that getting the terrestrial gravity data up in the hillsides that are covered in bush was too much. So they actually flew gravity surveys. I haven't got the map which shows the line spacing. It's typically tighter airborne line spacing than you would fly LiDAR. It requires a lot more processing than getting terrestrial gravity data. But in terms of data acquisition, it's much more rapid, and it's probably a good solution for Trinidad and Tobago. The other way is to do like they did in Australia. Levelling, which would be constrained, need to be constrained by a number of tide gauges, because that's the other problem. When they did the levelling in the late 1960s, they constrained it at one point. That was the mistake. What they really needed was tide data at 4 or 5 locations around the coastline. So then when you come to the adjustment, you're actually constraining it more often, and so you get your adjustment between the tide gauges rather than round the whole loop. So levelling with multiple tide gauges is an option, and I don't think it's a realistic option, because getting up across the northern range would be nearly impossible. This is what they did in Australia, because you can do it in Australia. Australia is flat. There's hardly any hills there. It's not really practical to do such a thing across Trinidad, and you would do it along the roads, and you would miss great chunks of the landmass. So I don't think this is really an option. I think gravity data is probably the best way forward through one of these two techniques. So gravity data was processed to give us the geoid, and at the same time you get some GPS information, and that gives you the geoid spheroid separation, and you can work on a model. If you then think about this normal orthometric correction thing that I spoke about, so somebody who wants to go and do some levelling and get some heights, absolutely, on the new Trinidad vertical data, could do so with GPS easily. GPS is not very good over short distances. Right? GPS is really good at giving you an accurate height in the middle of nowhere. But if you was to take 2 GPS points and look at them and compare them with a level, the GPS would not be so good, because the GPS has got more error in it. You're looking at about 2.5 centimetres in your GPS data vertically from short period observations. You'll get much better than that over short distances using a level. So ideally, if you want absolute height somewhere, you go out with a GPS, you put a mark in, and then you can level from there. And you should really be applying this normal orthometric correction, which is dependent upon things like height, azimuth, can't remember what else, various other factors come into this equation. If I take a height of around about 100 metres, and an azimuth on a north-south line, which is the worst case situation, the normal orthometric correction at low elevation of 100 metres is about 0.03 millimetres per kilometre. Nothing, right? Largely across places like Trinidad, you wouldn't even need to apply. You would just undertake your normal levelling exercises. Only if you were going longer distances, higher elevations, would you actually have to worry about this normal orthometric correction. So it enables people to work with both modern technology and levelling. Levelling is much better over the short distance, but GPS is much better in giving you an absolute value to start with. One more thing I should say, and that's everybody's talking about EGM 2008, which is a tunable model. This does exactly what I've been talking about, but it's not good enough. In its most refined form, EGM 2008 is available on a 1 minute by 1 minute grid. So it looks like it's got a lot of, it's highly precise in terms of its grid resolution, horizontal resolution, but actually it's not, because this is obtained from what they call a harmonic model, which considers undulations around a spherical surface. So the geoid is allowed to undulate, and the length of one undulation, the smallest whole sinusoidal undulation that EGM 2008 can represent is 1,800 meters.